Okay, let's unpack this. Imagine for a moment, you're a brilliant researcher.
Right.
You've been steeped in the deep learning Bible, like forever, the one that tells you unequivocally that for a machine to learn, its internal weights must change.
Right. That's the fundamental rule.
It's the law. And then these massive language models, these LLMs, they burst onto the scene and they just, well, they learn. In context. No weight updates needed. It's like gravity just decided to take a coffee break right in front of your eyes. You see them learn from just a few examples in a prompt, and, every fiber of your being screams, hold on, weights must update to learn.
That initial shock, that cognitive dissonance almost, is really central here.
Yeah. But then you look closer. You look at these transformers with their attention mechanisms plus those MLP layers stacked up.
That specific architecture.
And you realize you show the block tweaks MLP weights implicitly using the context. No training steps, just inference time magic. You prove it turns context into these low-rank updates under pretty mild assumptions, too.
It's a powerful insight.
Someone says, it's just memorization, maybe. But you point to the theory, the dynamics laid out clear. They say ICL is a mystery.
Which it genuinely felt like for a while.
But you unravel it step by step.
Yeah.
You realize you didn't just describe a feature. You uncovered how LLMs learn without training, a hidden mechanism working in plain sight, In that dance of attention and MLP.
The interaction is key.
They go quiet. And you realize you didn't just study in-context learning. You revealed the bridge between inference and learning, built right into the transformer's core.
And what's truly fascinating here is precisely that initial disbelief, the intellectual wrestling match you described.
Yeah.
The conventional wisdom, established in foundational texts really define learning as this dynamic process of explicit weight optimization.
You tweak, you train, you update. That was it.
Exactly. So when models like GPT-3 came along and really brought in-context learning, or ICL, into the mainstream, well, they clearly demonstrated this ability to adapt just from examples within the prompt itself.
Right there at inference time.
And it truly was a mystery. It was this emergent, dynamic reconfiguration happening without any explicit training steps. It really challenged decades of established understanding.
Exactly. It felt like some kind of inference time magic. Researchers were just staring at it, scratching their heads, saying, ICL is a mystery. But what if that mystery wasn't a flaw or some statistical fluke, but a hidden mechanism, something working in plain sight?
A fundamental property, perhaps.
Yeah, woven into the very fabric of these transformer architectures. What if you, our curious listener, could trace that understanding step by step, realizing that you're not just describing a feature, but actually uncovering how LLMs learn without traditional training. You're basically getting a shortcut to that aha moment. So today, our mission in this deep dive is to illuminate some really groundbreaking research. It's from Dherin, Munn, Mazzawi, Wunder, and Gonzalvo at Google Research, published just this year, 2024.
A very recent paper.
Right. And their paper is perfectly titled, Learning Without Training, the Implicit Dynamics of In-Context Learning. It finally gives us a solid theoretical and experimental explanation for this seemingly magical ability.
It provides a real mechanism.
Yeah. We're going to peel back the layers today and reveal the bridge, that connection between inference and learning that's built right into the transformer's core.
Sounds great.
So let's cast our minds back to the beginning, the core mystery of this inference time magic. For the longest time, learning in machine learning, it meant something very specific.
It really did. Explicit weight updates.
Exactly. You'd feed the model data, it makes a prediction, you measure the error, and then you adjust its internal parameters, its weights, through something like gradient descent.
The standard optimization loop.
That's how it learned. That's how it got better. So when these powerful large language models, LLMs, came along and started doing this seemingly impossible trick, adapting to new patterns just from examples given in the prompt.
It really did defy conventional wisdom.
And this was happening at inference time, when the model was just running, not during its, dedicated training phase.
Precisely. The mystery wasn't just that ICL happened, but how it could possibly work. When models like GPT-3 showed this so powerfully, the mechanism underneath was incredibly elusive.
Right.
Early on, there were several, compelling ideas. Some researchers proposed that ICL might just be capability retrieval.
Okay, what does that mean exactly? Capability retrieval.
Think of it like the model rummaging through its vast pre-trained knowledge. It finds the skill it already has that's most relevant to your prompt, rather than, genuinely learning something new on the spot.
Ah, okay, like picking the right tool from a giant toolbox it already has.
Exactly. Others suggested it was maybe a form of implicit Bayesian inference, sort of subtly updating its internal probabilities based on the context it was seeing.
And didn't some of that early work find something really weird? Something that made you question if it was really learning at all? I remember hearing that if you gave models examples with like random labels in the prompt, they didn't completely fall apart.
You're absolutely right to bring that up. That was a really puzzling finding. Some early results for certain models indicated that even when the labels in the prompt examples were randomly switched, total nonsense, basically.
Yeah, like cat means dog.
Right. The ICL performance didn't drastically decrease in some cases, and this, understandably, raised big questions about whether the model was truly learning a new function on the fly or just, I don't know, conditioning its output in some very sophisticated way without actually forming new internal representations.
Felt more like pattern matching, maybe.
Perhaps. However, it's really crucial to acknowledge that later, more advanced research did clarify this. It showed that larger, more sophisticated models do eventually start to learn from those randomly switched labels.
Ah, okay. So the bigger ones do adapt.
It indicates genuine on-the-fly adaptation is happening in those larger models rather than just, say, clever retrieval or simple pattern matching. This whole evolving understanding is exactly what researchers have been trying to pin down.
Okay, so that sets the stage perfectly for the big breakthrough. We had hints of implicit learning, but Dherin and his colleagues, they came at it differently, didn't they?
They did. Instead of just focusing on simplified toy models, which are useful but limited, or making strong assumptions about the transformer architecture that might not hold in practice.
Right, things like linear attention or only one attention head.
Exactly. They generalized the core concepts. They looked right at the heart of the transformer, that iconic block structure, the attention layer followed by the MLP.
The multi-layer perceptron, yeah, the workhorse.
And they saw something much, much deeper. Their really innovative approach was to introduce and formalize this concept of a contextual block.
Okay, contextual block. Let's break that down.
Sure. To really get it, we need two key new ideas they introduced. First, a contextual layer. Think of it like a smart filter. It doesn't just process one main input, it also intelligently incorporates context alongside that input, like the prompt or instructions. Exactly. The self-attention layer in a transformer is a perfect example. It processes a query token, sure, but its output is profoundly shaped by the instruction prompt or the preceding conversation. That's the context. It's like someone listening to you, but constantly adjusting their interpretation based on your tone or past interactions.
Okay, got it. Contextual layer. What's the second part?
Second, building on that is the contextual block. This is simply the composition of one of these contextual layers, like self-attention, with a standard neural network.
And in transformers, that standard bit is the MLP.
Precisely. The MLP is like the transformer's main processing unit after it's paid attention. This whole concept generalizes the traditional transformer block. It lets them apply their findings more broadly, potentially to other network architectures that have this kind of contextual property, not just transformers.
So it's a more general idea.
It's a way of saying, look, if a network layer can take context and then feeds into a standard processing unit, something profound can happen.
And here's where it gets really interesting, right? This is where they find that bridge between inference and learning.
This is the core finding, yes. Theorem 2.2 in their paper. It's a truly mind-bending insight.
Lay it on us.
It states that the combination of a self-attention layer with an MLP allows the transformer block to implicitly modify the weights of the MLP layer based on the context you provide.
Whoa, hang on. Implicitly modify the weight. So even though no actual gradient descent is happening during inference, no weights are physically being saved differently.
Correct. No explicit updates.
The MLP behaves as if its weights have been dynamically adjusted in real time by the context.
That's exactly it. It's like the model is temporarily rewiring a part of its own brain based on your prompt, and then, discarding that temporary rewiring once the prompt is processed.
That's wild, and they have math for this.
Oh, yes. It's not just a vague idea. They provide an explicit mathematical formula for this implicit modification. Their analysis shows that the effect of a portion of the context on the MLP's output corresponds to what they call a rank 1 weight update to the first layer of the MLP.
Okay, rank 1. That sounds technical, but why is that detail important?
Rank 1 is crucial. For listeners not deep in linear algebra, think of it this way. It's an incredibly precise and efficient kind of adjustment.
Not just changing everything randomly.
Exactly. It means the weight change is highly structured, very constrained. It can be expressed simply as the outer product of two vectors. It's like tuning a single very specific dial on a complex machine rather than recalibrating the whole thing.
So it's targeted.
Very targeted. The formula literally shows how the context you provide effectively transfers new information into the MLP's weights, making them adapt. It's an internal, temporary adaptation happening right there on the fly.
And you mentioned this wasn't just about transformers.
That's another incredibly powerful part of this finding. This mechanism, this implicit weight modification, seems to hold true for any contextual layer, not just self-attention.
Like what other types?
Well, it could potentially include architectures like recurrent neural networks or even, say, recurrent layers with local attention, like those found in some newer models like Griffin.
Interesting. So it might be a more fundamental thing about neural nets?
That's what it strongly implies. It suggests this isn't just some quirk of the transformer. It's a deeper property of how many neural networks can dynamically reconfigure themselves based on their input. It's a really deep insight into the nature of learning within these complex systems. Now, connecting this back to the idea of learning, what's truly fascinating is how consuming context tokens, one after another, reveals what they call an implicit learning dynamics.
Okay, learning dynamics.
Yeah, by iteratively applying this implicit weight update formula, the rank 1 thing, as each new context token comes in, a sequence of evolving context weights is effectively formed inside the model.
So it's like the model is updating its internal understanding, its effective weights, with each bit of info it sees in the prompt.
Precisely. It's getting smarter, in a way, about the specific task at hand, just based on the examples you gave it.
And here's where the full picture really comes into view, right? This iterative process, this sequence of internal adjustments, you're saying it is like gradient descent.
Their analysis shows it can actually be realized as a form of stochastic gradient updates.
Wow. Think about that for a second. So each context token you feed the model, it's not just data, it processes.
It acts like a tiny, immediate data point in an online gradient descent process.
Whoa.
The model is implicitly minimizing some kind of changing loss function at each step, almost as if it's learning from individual examples right then and there.
And does it behave like real gradient descent? Like, does it converge?
It does. Just like traditional gradient descent that converges towards an optimal solution, these implicit gradient updates, the marginal changes in the effective weights, they actually decrease and eventually vanish as more context is processed.
Just like you'd expect.
Exactly what you'd expect from a converging optimization process. But, and this is the kicker, it's happening without any explicit training steps, purely at inference time.
Mind blown. So others had suggested this link before, right? ICL as implicit gradient descent.
Yes, this builds upon some really important prior work. Several research groups had suggested this connection. However, a crucial distinction of Dherin et al.'s work is that they rigorously proved this without many of the limiting assumptions made by earlier theories.
Like needing linear attention or single-head attention.
Exactly. Those assumptions made the math easier, but didn't really match complex real-world transformers. This new work removes many of those limitations, bringing the theory much closer to how actual large transformers operate. It makes the analogy to gradient descent far more robust and, frankly, more believable.
That's truly compelling. Okay, so the theory sounds amazing, very elegant, but the ultimate proof of the pudding, as they say, is in the eating. How did they test this? How did they make sure it wasn't just, a clever mathematical trick?
Right, the experimental validation is key. The authors verified their theory using a transformer trained on linear function approximation tasks.
Okay, so learning simple linear relationships.
Yes. It's a controlled but still representative setting that other researchers had used before to study ICL, so it serves as a reliable benchmark. It allowed them to really isolate and measure the effects they were theorizing about without too much other complexity getting in the way.
And what was the smoking gun? The definitive proof.
Here's the really cool part. The moment that solidified their findings, the experiments showed that predictions made by the trained model when it was given an in-context prompt were identical.
Identical. Not just similar.
Identical to predictions made by the same model if its MLP weights were explicitly modified according to their derived formula, but without seeing the original context.
Wait, let me get this straight. Option A, give the model the context. Option B, don't give it the context, but manually tweak its MLP weights using their formula. And the output is the same.
Exactly the same. The loss values they measured for both setups were in remarkable, almost perfect agreement. It's like saying, you gave me an instruction, and I behaved precisely as if I had rewritten a piece of my brain to follow it, even though I didn't actually change anything permanently. It's really powerful evidence for this implicit dynamic rewiring.
That's incredible. And did they also check the gradient descent part experimentally, the vanishing updates?
They did. Their experiments provided strong empirical support for that analogy, too. They observed that these implicit gradient updates, the marginal changes in the effective weights, did indeed decrease and vanish as more context was provided.
Just like the theory predicted.
Just like the theory predicted for a converging optimization process. It visually confirmed that the model was settling into a stable, adapted state based on the context. Now, while the implicit weight update dynamics are distinct from, say, explicit fine-tuning using standard stochastic gradient descent.
They aren't exactly the same process.
Right. But the experiments confirm that they effectively minimize the loss in similar ways. This highlights a kind of functional equivalence, even if the mechanism isn't identical, between ICL and traditional learning. And that's a massive conceptual leap. This research really represents a profound shift in how we understand what's going on inside these networks. It suggests that in-context learning is maybe less about the specific magic of self-attention itself.
Which is what a lot of people focused on initially.
Exactly, and more about this fundamental fact that regular neural networks, particularly this combination of a contextual layer and an MLP, have an inherent ability to transfer modifications from their input space, a context, directly into their effective weight structure.
So it's deeper than just attention.
That's what it seems. What's truly fascinating is that this implies it isn't just some unique trick of the transformer. It might be a deep property of neural networks themselves, possibly connected to why they generalize so well across different tasks. It connects to broader theories about how networks form internal representations and adapt on the fly.
That's a truly profound realization. It changes how you even think about these models. But okay, like any groundbreaking research, it's important to understand its limits, right?
Yeah.
What are the acknowledged boundaries of this analysis?
Absolutely. And the authors are very clear about this. Firstly, their derivations are primarily valid for a single transformer block.
Okay. But real models stack lots of these blocks.
Precisely. So their current theory doesn't fully capture the complex, cascading interactions and dynamics that happen across multiple stacked blocks, which is, of course, how all the really large, powerful LLMs we use today are built. That remains an open question.
Makes sense. What else?
And importantly, the main theorem primarily analyzes the effect of the context on the output for the very last input token that's processed.
So like the answer to a question, but not necessarily how it generates a whole paragraph after that?
Right. It doesn't fully capture the entire sequence generation process or the intricate ways information propagates and affects the generation of subsequent tokens beyond that initial response. The full dynamic flow across, say, an entire generated essay or conversation is still an area for further theoretical exploration.
Okay, understood. But even with those limitations, what Dherin and his team have done here feels like a massive leap forward.
Oh, absolutely.
It's like they've peeled back a significant layer of mystery from these incredibly complex systems. They've moved in-context learning from being this sort of emergent magic.
Something we observed but couldn't explain.
Exactly. To a theoretically grounded, experimentally validated mechanism. It demystifies a core capability of LLMs in a really powerful way. So what does this all mean for you, our curious listener? We've gone from in-context learning being this mysterious emergent property, almost like a magic trick, to understanding that LLMs are literally learning without training.
In a very real, mechanistic sense.
Oh, yeah. They're performing these sophisticated implicit weight updates, especially targeting their ML key layers right there at inference time, based purely on the context you provide. It's not just memorization, not just capability retrieval. It's a dynamic gradient descent-like process happening under the hood. This isn't just describing a feature, it's uncovering how LLMs learn without traditional training. It reveals that fundamental bridge between inference and learning built right into the transformer's core.
It really unravels a major theoretical puzzle that has stumped researchers for years. It reveals this deep fundamental property of how neural networks can dynamically reconfigure based on input, bridging that divide between inference and learning in a way we just hadn't fully grasped before.
Yeah.
It truly shows the incredible depth and adaptability built into the transformer's architecture, working right there in plain sight. It proves these models are far more dynamic, far more adaptive than maybe we initially gave them credit for.
So, here's a thought to leave you with. If LLMs are already performing such complex implicit learning during inference, adapting to new information on the fly with every single prompt you give them, every conversation they have, what does this imply for the future of AI development?
Where does this capability lead?
Exactly. Are we maybe on the cusp of truly self-adaptive, perpetually learning systems, systems that don't need constant, heavy retraining cycles, but can actually change and evolve their understanding with every interaction right out of the box? What does that future look like?